Hello, welcome to lesson 5 from chapter 9, year 2, pure mathematics. Today we're going to look at differentiating parametric equations. And you've already met parametric equations in chapter 8. So now we're going to apply our differentiation rules to parametric equations. So I've given you some standard results that you may find useful here. Okay, please familiarize yourself with those. And we've also got the differentiation rules, the chain rule, the product rule, and the quotient rule, which you've been practicing quite extensively. So please pause the video and have a go at the 4 warm-up questions. Okay, and let's have a look at the solutions. Okay, so for question 1, we're given a curve C1 in parametric form, and we're asked to find two derivatives, dx by dt and dy by dt. So x, as you can see, t plus 1 over 2. If it's easier, it's up to you, of course. We can write that as 1/2 of t plus 1/2, dividing both of those terms in the numerator by 2. And if we want to find the derivative, we simply differentiate x with respect to t. So we differentiate t, half t and a half term by term. Okay, so dx by dt is simply going to be 1/2. Okay, as we just take the coefficient of t here, okay, and the constant 1/2 is lost. So that's dx by dt. Now for dy by dt, we've got t squared plus 1 is what y is equal to. So if we differentiate that, we're simply going to get 2t, and again the constant term dies. Now for part C, we're asked to state the range of C1. Now the range, of course, relates to the y values. Okay, so the range, in other words, is which y values are we going to get out of this? Well, if you look at the range of t, which is our parameter, we can see here we're allowed to substitute in all real numbers. So when I'm thinking about the range of C1, I'm thinking about this part only. I don't have to bother with the x parametric equation because that's the domain. Okay, so we just have to focus on the y values. So what y values am I going to get out of this when I can substitute in all real numbers? If you're not sure, one way to do it is to just sketch the curve. Okay, so I'm just going to do this. So we'll have a t-axis here. We'll have the origin and we'll have the y-axis. So remember, y is a function of t. And if we have t squared plus 1, well, it's a quadratic shifted up 1 unit. So I could draw it like this, perhaps, something like that. Obviously, you don't have to do this. This is just me explaining the ideas. Okay, so it's got a y-intercept at y equals 1. And you can see very clearly now, if we look at the possible values of y, well, anything greater than 1 and equal to 1 is valid. So that's our range. So we can just write that down. And you could have written that down straight away, but I just wanted to go through the concept with you. So y is greater than or equal to 1 would be sufficient. Okay, so that's question 1. Now, for question 2, we have to find a Cartesian equation for C1. I've put that in italics. So remember, Cartesian is x and y. Okay, so an x variable and a y variable. X is independent, y is dependent. How are we going to get a Cartesian equation for C1? Well, we've seen this in chapter 8. We look at our two equations. So we're going to consider x is t plus 1 over 2 and y is t squared plus 1. And we're going to try and make t the subject in one of those equations. So I'm going to call the x part equation 1. I'll call the y part equation 2. So in equation 1, so we're going to make t the subject. Now, making a particular letter the subject will eliminate it when you have what we could say simultaneous equations in a sense like this. So make t the subject, because that's what we want to eliminate. Okay, there's no t variable here or here. Okay, just purely x and y, so we'll make t the subject. So let's do that. So we're going to have 2x, just multiplying both sides by 2, is equal to t plus 1, which implies that t is equal to 2x subtract 1. So we've now got t as our subject. So now we're going to sub this in 2. So we're going to sub t equals 2x subtract 1 in equation 2. Okay, and this is nice and simple. So if we do that, we're going to get y is equal to, and I just replace t with all that. So it's going to be 2x subtract 1 all squared plus 1. And you can leave it like that if you want. There's nothing wrong with that at all. We're not asked to write it in a particular way. We're simply told to write it in Cartesian form. And we know this is Cartesian form because the only variables we have that we can see are x and y. It doesn't matter whether y is a subject or not. They just have to be in terms of x and y. Okay, and now we have to show that C1 has a stationary point when x equals 0.5. Okay, well, stationary points. Well, if we want to find a stationary point, this going way back now, how do we do it? Well, we have to use this property. dy by dx is equal to 0. Okay, so we need to find the gradient. Now, dy by dx, we've got dx by dt, dy by dt. We'll be looking at how to use those a bit later on. If we just go for dy by dx directly, using what we've just worked out here, okay, we should be able to do that. So what you can do is you can either expand the whole thing, or we can use the chain rule. So I think I'm going to use the chain rule here. We're just going to do it really quickly. So we've got dy by dx. Okay, now for the chain rule, I bring the power down, that's here, to the front. Okay, and subtract 1 from the power of the brackets. That's going to be 2x subtract 1 to the power 1. And then I multiply that by the derivative of everything that is inside the bracket here. Okay, that would be the u substitution. So I have to multiply all that by 2. Okay, and the plus 1 obviously will go. Now, if you didn't like that, of course, what you can do, if that's not something you're keen on doing, or you didn't follow that, if you expand the whole thing, you're going to get 4x squared, subtract 4x, you're going to get plus 1, and then plus another one, so that's going to be plus 2. Okay, and if you differentiate that, you're going to get hopefully the same thing. So let's just expand this. So this is going to be 2 times 2 is 4, times 2 is 8x, minus 2 times 2, which is minus 4. Okay, and you'll get the same thing here. If we differentiate what I've just expanded here, you should get the same thing. Okay, so just to check that, you can use whatever technique you like. So now if we set all that equal to 0, so at stationary points, please write this every time you're using this property, okay, to show that you understand. dy by dx is equal to 0. So therefore, 8x subtract 4 is equal to 0, which implies that x obviously must be 4 over 8. So x must be 0.5. Okay, and we've just verified what we had to show. Okay, so if it says show that C1 has a stationary point when x is 0.5, that's one way to do it. Another way would be to sub in 0.5 into dy by dx, and you'll get 0, and that also verifies it. So there's two approaches there. Okay, so in questions 3 and 4, we've got a similar framework, really. We're going to look at parametric equations going into Cartesian equations, but this time we're dealing with trig functions. So once again, I'm going to have to find dx by d theta in this case and dy by d theta. And if we look at x, it's 1 plus cos theta over 3. So again, if it's easier for you, if you write that as 1/3 plus 1/3 cos theta, maybe that will make it easier to differentiate. Okay, so that's just what x is equal to. If we differentiate this, obviously the constant term will disappear. And if we differentiate cosine, that's a standard result. So that's going to be negative sine. So that's going to be negative 1/3 sine theta, keeping that coefficient at the front there. Okay, so that's dx by d theta. For dy by d theta, it's cos 2 theta. Just be careful with this. Read the question really carefully. We now have cos 2 theta. So if we differentiate that, obviously the standard result means that the 2 inside that function is extracted. It becomes a multiplicative constant at the front. So that's going to become 2 multiplied by, I'm just going to build this up. So that's going to be 1/2. And because it's differentiating cosine, it's all going to be negative. So, and sine 2 theta as well. Okay. So just to simplify that, this is going to be minus sine 2 theta. Okay. I hope that makes sense. Now, for part C, we have to state the domain and the range of C2. Now, I'm just going to create a bit more space here. I've just boxed this off. The domain and the range. Now, this is quite interesting when we're talking about parametric equations, because we have a bounded range of theta. It's 0 to 2 pi. And the x variable is in terms of theta. Now, if I take my x variable, I know that my cosine part, which is here, is bounded. Okay. Now, how is it bounded? Well, if we just write down the bounds of cosine, we know that cosine is bounded between -1 and 1 inclusive, between 0 and 2 pi, because there's a full cycle of cosine within those within 0 to 2 pi. So those are the bounds of my cosine. Okay. Similarly, cos of 2 theta is also bounded. Okay. The 2 just increases the frequency. Just to sort of slip into physics a little bit there. But the cos 2 theta does nothing to the range, okay, of cosine. It just means that it's more frequent, okay? So the period is doubled. Oh, sorry, the period is halved. So those are the two tools we're going to use for this part. Now, to get the domain and the range, we can just apply these two pieces of information. So the lower bound for the domain. So I'll just start with the domain. So the lower bound is when I'm using -1 here. Okay. So that should be pretty straightforward. That means x would simply equal 1 subtract 1 all over 3, which equals 0. Okay, using the lower bound. And for the upper bound, I'll just change colors here. I'm going to plug in 1. So x would equal 1 plus 1 over 3, which of course equals 2/3. So by putting restrictions on cos theta, we also put restrictions on x and consequently y, which we'll see in a minute. So we can now say that the domain is going to be, all x values will be between and including 0 Okay, and this is where we've got to be careful. So 2 theta is not allowed, okay, but it will hit its maximum before it reaches 2, beg your pardon, 2 pi is not included, but cosine will hit its maximum before it gets to 2 pi. So the maximum bound is going to be 2/3, and that is inclusive as well. Okay, I hope that makes sense. You can basically, you could sketch the graph as well, and you can see that that's the case. All right. Now for the range, we can use a similar argument. So for the range, we just apply the same restrictions, but on the y value this time. So if we start with -1, okay, and I realize I'm running out of room, so I'm just going to do it down here. Okay, so for the range, okay, let's do the lower bound first, is -1. Well, that just means that y is just going to equal -1/2, because the cos 2 theta part here is just going to be replaced with -1. And then the upper bound, y is simply going to be the cos 2 theta replaced with 1. So that's going to be +1/2. Okay, so let's write down the range now. So anything between -1/2, y, and +1/2. Okay, so there's a little bit of thought going into that. If you're not sure, plot the graphs of x and y on Desmos. You'll be able to see, or GeoGebra, whatever it is, and you'll be able to see that unfold in front of you, and you can look at the extremum values. Right, okay, moving on to question 4. We have to show the Cartesian equation again. So just in terms of x and y, as you can see, has that particular form. Right. Now, this is where it gets tricky. Making theta the subject would be a pretty difficult task here. But what we can do is we can, in the equation for x here, we can make cos theta the subject. Okay, so I'm going to do that. And we've discussed this previously, so I won't labor it. So in equation 1, I'm going to make cos theta the subject. Okay, so it's a bit of an instruction, an annotation. Now, if we do that, we're going to have, so therefore 3x is going to equal 1 plus cos theta. Okay, which implies that cos theta is equal to 3x subtract 1. Now, notice something here. This is a good sign because we've got the 3x subtract 1 here and here. So we can see that that's going to be squared. So why is it squared? Because we can't see any squared terms over here. And we're going to have to bring y in now. So how does this work? Well, what you've got to do, this is where you've got to use your brains a little bit, is you've got to look at the equation for y and think, how, I'm going to write it out, how do I replace the cos 2 theta, because it is cos 2 theta. I can't just swap cos theta and cos 2 theta. I've got to replace it correctly. How do I replace this with something in terms of cos theta only? So we go back to our identities. Please remember your identities. You learn them and write them on flashcards, stick them on your toilet door, but make sure they are ingrained so that they jump out at you when you get to situations like this. So cos 2 theta, okay, in terms of cos theta. That's what we want. Can we do it? Well, yes, we can. So recall that cos 2 theta is identical to 2 cos squared theta subtract 1. Okay, so there we can do a straight swap. So if I go back to my y equation now, so therefore y is going to equal 1/2 multiplied by all that. So it's 2 cos squared theta subtract 1. And we'll put that inside blue brackets as well. Now, if you notice, the half and the 2 will cancel. So this is just going to be cos squared theta subtract 1/2. Okay, and you could have substituted in earlier. I'm gonna do it now. So this is going to be cos theta is going to be replaced by this, which I've done earlier, by this thing. This is what cos theta is in this situation. So it's going to be 3x subtract 1. I'm going to square all that and then subtract 1/2. Okay, and there we have it. So that's the thing. When we have a trigonometric parametric equation situation like this, you make the trig function the subject, the cos, the sine, whatever it is, and then you substitute that into the second equation using a trig identity. Okay, that's the way to go. Don't use things like an arc cos or an arc sine. You'll just get into a real mess. Now we have to find dy by dx, and we can do this using our Cartesian form and using standard results. Okay, so once again, I'm going to use the chain rule here. So dy by dx. So I'm going to use the chain rule in its quicker form. So I'm going to bring the 2 down to the front. I'm going to subtract 1 from the power of 3x minus 1. So that's going to become 3x minus 1 to the power 1. And then I'm going to multiply the whole thing by the derivative of what's in here, which is what the chain rule does. Okay, so it's going to be that. And obviously the minus a half term will be gone. And the nice thing about doing this is, of course, you get your answer in a really nice factorized form. So this is simply going to be 6 lots of 3x subtract 1. If you use the different technique, just check that you agree with the solution here. Okay, so that concludes the warm-up. Okay, so today, as I've said before, we're going to look at parametric differentiation. And you already have the skills to do this. It's just applying these skills to a new context. Now, I've gone back to to warm-up question 1, as you've seen already. We've got 2 equations, one for x, we'll call that equation 1, and one for y, equation 2. And you've already done the derivatives. I've just put those in again. So we have dx by dt. Remember that we're differentiating the variable x, which is the subject here, with respect to the variable t. So that's why we have dx by dt. So x variable on the left-hand side purely, and t variable on the right-hand side, again, purely or exclusively. And also dy by dt, so we've got the y variable here, and then everything is in terms of t on the right-hand side. And the derivatives are, of course, are half and 2t respectively. So beneath that, I've just stated that we can construct dy by dx using the chain rule. And you know how to do this because this is the key fundamental principle of the chain rule, isn't it? If I want to construct dy by dx, if I just write it out first, dy by dx, I have to have a derivative, first of all, with dy in the numerator. That's essential. And then I look at the raw materials that I've got. What have I got to work with? Well, the only one I can use, which has a dy in the top, is this one. Okay, so I'm forced to use this. So it's got to be dy by dt. All right. So I'll put that in. Okay. And what else do we need? Well, we need a dx in the denominator. Right. Do we have that? Well, we can, how can I phrase this? Well, we've got half of what we want, haven't we? Okay, we're partially there. We've got dx by dt. So it's not quite what we want. I want the dx in the denominator. So what I can do is I can say, all right, I'm forced by the situation I'm in I'm forced to cancel out the dt's because that's the variable we're not using. But I'm going to have the dx in the denominator. So the question is, can I get dt by dx from what I've got here? Well, yes, because both of these are just reciprocals of each other. Okay, so it's not a problem. If I reciprocate 1/2, which is 2, I've got my dt by dx. So let's just complete our derivative. So it's just going to be dy by dt, which we know is 2t. Okay, multiplied by 1/, I'm just doing this for completeness. I know you can reciprocate 1/2, but 1/(1/2). Okay, which is equal to, of course, 2t multiplied by 2, which is, of course, 4t. Now, looking at that, does that look like the answer you got in warm-up question 1? Or question 2, I believe, wasn't it, when we actually differentiated it? Well, the answer is no. The derivative is in terms of t, but that's okay because t, we can substitute in values for t. So it's something we can evaluate, no problem. If you want to check that this is actually correct, remember what we can do is we can rearrange the first equation. We can go back to equation 1 here and make t the subject. Okay, so you can do this as an exercise. You can just pause the video and have a go at this if you want to. If I make t the subject, remember what we got? We got 2x subtract 1 is equal to t. Okay, and my derivative is 4 lots of that. All right, which is exactly what we got in questions 1 and 2. So there we have it. So that's how we construct dy by dx. So we have to reciprocate the dx by dt, but using the chain rule, it makes complete logical sense given the context and what we're in. So let's apply this to what was warm-up questions 3 and 4. We're going to differentiate x and y, and this time they are trig functions. So if we do that, and again, if you want to do this yourselves, just pause the video, go through the stages, and then just check that you agree with me once you've unpaused it. So we're going to do dx by dt first, but before I do that, I'm just going to write x term by term. So that's going to be 1/3 plus 1/3 cos theta. Okay, so dx by dt, sorry, beg your pardon, dx by d theta, I should say. The parameter is theta this time. So that's going to be negative 1/3 sine theta. Okay, and then just over here, dy by d theta, as we saw earlier, is going to be negative sine 2 theta. Okay, just doing that again because I don't have the answers right in front of me. Now, to construct dy by dx, so therefore, dy by dx, well, I'm going to keep the dy by d theta as it is. Okay, nothing wrong with that. Dy by d theta is here. So let's write that out. So equals dy by d theta, no change. But I'm forced, I can't have the d theta as part of this derivative because that's not the variable we want. So I'm forced by the situation to put d theta in the numerator. Okay, I'm also forced to put a dx in the denominator. Okay, this is what has to happen. Otherwise, it simply isn't going to give me dy by dx. So it's got to be d theta by dx. Okay, and just to remind you, of course, this is the reciprocal. So this and this are reciprocals of each other. So just don't forget to reciprocate the dx by d theta. So let's finish that off. So this is going to equal negative sine 2 theta multiplied by the reciprocal of that. So that's going to be 1/, And be careful with this, please, ladies and gentlemen. So that's going to be minus 1 over 3 sine theta. Notice I put the whole of dx by d theta in the denominator. We have to reciprocate it. Now, let's just look quickly at what happens here. I've seen several mistakes with this. You have 1 over negative 1/3. Okay, well, we know that's going to be negative, and obviously 1 over 1/3 is going to be 3. So we now have 3 in the numerator. Okay, and it's negative. So we also have another negative at the front, multiplying the sine 2 theta, so that's going to be positive. So this whole thing becomes positive because of the double negative. So that's going to be 3. And then we've got sine 2 theta over sine theta. Okay. And again, you might be thinking, well, this doesn't look like what we had earlier. So in this situation, we can use trig identities. Now, if you notice, this doesn't look like the original answer. But what I can do is I can replace the sine 2 theta with something else. Okay, so this I can make a substitution because it's part of an identity. So if I replace this with what is essentially going to be 2 sine theta cos theta, okay, and if I multiply all that by 3, of course, that's going to give me 6 as the coefficient here, okay, and that's all going to be over sine theta, okay, and then the sine thetas, of course, will cancel, and we'll simply be left with 6 cos theta. Okay, now once again, you'll be thinking this doesn't look like the original answer, it's in terms of theta. Well, we can employ the same trick that we employed, well, it's not a trick, but the same technique that we employed in the first example. Notice I can just make cos theta the subject in equation 1, which I haven't called equation 1, but I'll do that now. So we'll call this equation 1, we'll call this equation 2. Okay, and if I rearrange equation 1, we're going to get 3x, okay, and then that's going to be subtract 1. All right, and if I multiply all that by 6, you can see that it's exactly the same as what we got previously. Okay, so 6 lots of 3x subtract 1. So although the derivatives, if you do them as dy by dx in Cartesian form, and then compare your results to parametric form, they may not look the same. It's highly likely that they won't, but they are the same. They're just expressed using different variables. Okay, so that's the idea. So it's using the chain rule, but there is a reciprocation that needs to be done. So let's look at the general form of this, and then we can do some examples. So more generally, it says if x and y here are functions of a parameter t. So in other words, we define x in the following way. Let's get rid of that. X is a function of t, so we tend to write it like that, like f of x. X is a function of t, and y is also as a function of t. Then the derivative, dy by dx. So put this in the box. This is really an important result here. It's simply going to be dy by dt, which we've just seen, multiplied by dx. No, dt by dx, I should say. Now, if you do a bit of research on this, that's the way I've done it. Another way to express this would be to say, okay, well, this is the same as dy by dt multiplied by 1 over and I'll write it as dx by dt, the reciprocal. Okay, and even further, you could even say, and perhaps this makes even more sense, I don't know, this would be equal to dy by dt divided by dx by dt. Not giving myself enough room there. Okay, they are all equivalent statements. So there's different ways of thinking about it. The way I've done it is multiplying by the reciprocal, of course, which was the first bit, reciprocating dx by dt. Or you could, rather than reciprocating, just write it as 1 over and then reciprocate. Or perhaps you prefer this way, where you say dy by dt divided by dx by dt, which does exactly the same thing. Okay, so they're all valid and they're all equally good. So let's have a look at some examples. We're going to have a go at differentiating some parametric equations and in some slight context as well. So for worked example 1, we have to find the gradient at a particular point P, where t is equal to 2. We mustn't forget that. And we've got this curve expressed parametrically. Okay, and just keep an eye on the range of values of r. The range of values of t, which in this case is all real numbers, which is why I said r by mistake. All right, let's go straight into it. So the gradient at the point P. So we need to find here what dy by dx is. Okay, and there's various ways of doing that. So let's go straight for it. So we've got dx by dt first of all. Let's differentiate that one. Again, if you want to do this, just pause the video and try it yourself. Okay, so this is going to be 3t squared plus 1. Okay, and then we've got dy by dt. I'll do that over here, which is equal to 2t. And then the plus 1 will go. So there we have it. Now, it says find the gradient at the point P, where t equals 2. Now, I've said earlier that when you're finding the gradient, you're looking for dy by dx. But because we're looking for the gradient at a particular point when t equals 2, you'll notice that I can just sub t equals 2 directly into both of these derivatives. Okay, so in other words, I can find dx by dt at point P and dy by dt at point P, and then I can find dy by dx later. So I'm going to do it like that. I think that's a good way to go. So let's say when t equals 2, we have dx by dt. Simply going to be 3 lots of 2 squared. So just change colour there to show I've substituted it in, plus 1. Okay, that's the derivative of t cubed plus t, which of course is going to be 3 lots of 4, which is 12 plus 1, which is 13. Okay, and we can also find dy by dt now. So dy by dt, which is just going to be 2 lots of that, so 2 lots of 2, which is of course just 4. Okay, so we've got those 2 values. We've got dx by dt and dy by dt. So now we're going to use our new information. Okay, so the gradient at P when t equals 2, okay, dy by dx is simply going to be, well, depends how you want to do it. It's going to be dy by dt multiplied by dt by dx. Again, you can do it whatever way you want to. It doesn't really matter. Okay, so dy by dt is of course 4 multiplied by, now dt by dx is the reciprocal of this one, the reciprocal of 13. So I've got to put that as 1 over 13. Okay? Which is, of course, just 4 over 13. So without actually talking about the gradient as dy by dx in terms of just x, we've got the gradient at that point straight away. And you can probably tell if you've got dy by dt here and dx by dt here, you simply just divide the 4 by the 13. Yeah, so you can just write down the answer in that sense. Okay, but I'm just using the formula or the what we've just derived earlier. So that's the first example. So now let's have a look at a trigonometric version of this. Okay, so in our final example, this is a trigonometric variance on what we've just done. So this time we need to find the equation of the normal, right? So again, we're building in some year 12 stuff here, the normal, okay? And the point we're interested in is where theta is equal to pi over 6. So for the normal, we've got the parameter, and we also need the gradient, okay? Obviously, because we're differentiating. So let's go ahead and differentiate, and we'll put it all together. So we have dx, this time by d theta. Okay. Again, if you want to go ahead and do this, please pause the video, check that you agree once you've done it. So derivative of sine is, of course, cos. So that's going to be 3 cos theta there. Okay. And then dy by d theta is going to be negative 5 sine theta. Okay. So our derivatives are done. So now we need to figure out what dy by dx is at this particular point. Okay, so there's various ways we could do this. All right, I'm going to get an expression now for dy by dx because we haven't done that yet. So therefore, dy by dx is simply going to be dy by d theta multiplied by d theta by dx. Okay. So this is going to be 5 sine theta multiplied by the reciprocal, which is going to be 1 over, just to show that I've reciprocated this, that's going to be 3 cos theta. Okay. Now we can also use an identity here. Remember, of course, we've got a sine theta, which is going to be divided by the cosine of theta, and we've got 5 over 3. So we're going to get 5 thirds tan theta. Okay, if you just want me to just remind you of that identity, we'll just put it here. So remember that tan theta is identical to sine theta over cos theta. All right. So I've used half the space here just to get that expression. So now we need to figure out what dy by dx is when theta is equal to pi over 6, which is, of course, what we're given here. So let's write that as a statement. So when theta is equal to pi over 6, dy by dx is simply going to equal 5 over 3 multiplied by the tan of whatever, well, of pi over 6, and we just have to figure out what that is. So just put that substitution in orange there. So we need tan of pi over 6. Okay, and if you're not sure, let's just put that in. So we'll just make sure you set on radians. So the tan of pi divided by 6. Should know this really, but okay, so that's root 3 over 3, or 1 over root 3 you might get. All right, so we can write that in. So don't forget that it's multiplied by 5 over 3. So it's going to be 5 over 3 multiplying root 3 over 3. Like that. So this is going to equal 5 root 3 over 9. Okay, and I strongly urge you to write it in the exact form there. So that's the value of the gradient of the curve at that point where theta is equal to pi over 6. We've just stated that explicitly. Okay, now we can get on to finding the equation of the normal. Now, what we need to do at the moment is we need to find out what actually is the x value at p and the y value at p when theta is pi over 6. We haven't actually done that yet. So for the normal, let's just make a note of what we need. So for the normal, I'm just going to have to get rid of this calculator. So we need the reciprocal of, I should say negative reciprocal. I apologize. So undo that. I'll just erase it. So we need the negative reciprocal of 5 root 3 over 9. Okay, and we also need an x value and a y value. Okay, now in a non-parametric setting, you would either get those or you'd have to figure out one of them using the Cartesian equation. Here we just sub pi over 6 into this one, we'll call it 1, and this one here, we'll call it 2. Okay, so the x value is going to be 3 sine of pi over 6. Okay, and once again, if you don't know what that is, just grab your calculator. Nothing wrong here. If you don't know what it is, don't worry. Okay, it's sine of shift pi divided by 6. Okay, so that's just a half, isn't it? It's a standard one. Okay, so fill that in. So it's 3 lots of a half, which is 3 over 2. So we've now got the x coordinate. Now for the y coordinate, do the same thing. We just sub it into the equation for y. So y is going to equal 5 cos of pi over 6. So again, we'll just do that really quickly. Cancel. So cosine of shift pi divided by 6. Make sure you're in radians, of course, that's root 3 over 2. So it's multiplied by 5 as well, sorry. So it's 5 multiplied by root 3 over 2, which is, of course, 5 root 3 over 2. Right, so we've now got all the ingredients. We can now put everything together. I'll just put a partition here so we don't get muddled up. Now, the equation, obviously, of a straight line, we would take y, subtract the y coordinate, is equal to the gradient multiplied by x, subtract the x coordinate. Okay, it's the most useful form in this situation when you've got the gradient and the pair of coordinates. Right, so for the equation of the normal, it's my shorthand for equation. So we're going to have y, subtract the y coordinate, which is, of course, 5 root 3 over 2, is equal to the gradient. Now, just remember, of course, we've got to be really careful. We haven't done the negative reciprocal of this yet, so I'm going to do that now. Okay, negative reciprocal of that. So this is simply going to be minus 9 over 5 root 3. Okay, multiplied by x, subtract the x coordinate. Right, I'm going to do that just to be consistent. So it's going to be x subtract the x coordinate, which is root 3 over 2. No, it's not. It's 3 over 2. All right. Now, that is the Cartesian equation of the normal. Now, it doesn't ask you to write it in any particular way. So that's fine. That will get you full credit. Obviously, you've got a root 3 in the denominator here. That should really be rationalized, but we've answered the question because we've got Cartesian. We've got x variables and y variables. So there's nothing wrong with that. So that would essentially do the job. But bear in mind, questions may ask you to write the normal or the tangent, whatever it is you're looking for, the straight line, in a particular fashion. So just be aware. Okay. If it doesn't, you can leave it like that and get full credit. Okay, so that concludes differentiating parametric equations. Please try the exercise and best of luck.